All right, I think we'll get started. We're going to talk about cryptography today using the .NET framework. And my name is Robert Boedigheimer. A little bit about myself. I've been a web developer since about 1995, so I'm primarily my day job as a full-time ASP.NET developer. I'm also a Pluralsight author. I've got a few trial cards that I've got a full course on cryptography there. If you're interested, you can stop up afterwards. I gave my blog, my email, my Twitter information. I also turned in the slides, and all of this code should be available on your USBs. Okay? But if you do have any questions as we go, feel free to ask. Things we're going to go over today, just talk a little bit of background about cryptography. We're going to go into hashing and how that works, symmetric algorithms, asymmetric algorithms, talk about how to use digital signatures. We're going to also talk about protecting your web.config file with cryptography so you can encrypt sections of it. We'll talk a little bit about key size and storage. How do you make the choices about what you're going to use? And then I'll mention some other .NET cryptography that's available. So a little bit of background. So the idea of cryptography, it's the science of keeping your messages secure. And we're going to focus really on, there's 4 different reasons why you might use cryptography, and it's important to understand which one you actually want, because that's going to help guide which one of the choices you're going to use, which technology within cryptography. So the one most people are familiar with is confidentiality. So the idea is that I want to be able to protect my data from being read. So for whatever reason, credit card numbers, things I don't want people to see, I'll use confidentiality. Integrity is when I want to verify that something has not been modified, and I'll show you some good examples of that. Authentication is where I want to identify and validate who a user is. And then non-repudiation is where I want a sender can't later deny that they sent a message, so we'll get into that with digital signatures. And the namespace we're going to use in .NET is System.Security.Cryptography. As I said, I'm an ASP.NET developer, so the examples I'm going to show you happen to fit in ASP.NET and happen to be web examples, but the same cryptography applies to any .NET code, so it really doesn't make a difference. Okay. Long list of considerations, so things that you need to worry about when you're looking at using cryptography. What's your goal again? Understand what it is you're trying to do, because that's going to map into the techniques you want to use. You need to understand how much your data is worth. So in other words, when we start talking key sizes and other things like that, if you need to protect your data for a long time, or if it's really important data, that's going to have you ratchet up the key sizes and be more secure, if that makes sense. We're going to consider what your primary threats are. So when you do threat modeling, like I would do for a website, I'd list out all the things I would be concerned about. Obviously, my data going in transit over the internet would be a concern for me. Whether I think people could access my web config file. So I'm going to talk later about how do you encrypt your web config file. If you're afraid somebody could get access to your web server and look at that file, I wouldn't want to have keys sitting in that file if I think people can do that. My personal stance, I treat my web servers in my DMZ like they're compromisable. In other words, I assume someone's going to be able to take over that web server, gain access to everything that's on it, and that's kind of the stance I take when I do security. Are you afraid somebody could dump out memory? I'm going to talk later about things that you store in memory. If someone can get on your machine and do a process dump, they can actually look at all of that data. So we'll talk about some ways to protect against that later. Can people modify pages? Can people reverse engineer your assemblies? If they get access to your assembly DLL and you put your password in clear string, for instance, they can just use ILDASM or any of the reflection tools and directly see all of your stuff. So it's important to sit down and think, for my site or for what I'm doing internally, which one of these things concern me so that you can make decisions about how you want to apply the right cryptography. Yeah. Obviously, I have company security policies, so I have a lot of policies about how we handle the data internally. Regulatory compliance, so I have to deal with PCI as a public-facing e-commerce website. And then layered defenses. How many do you think is enough? I'm going to talk about different things you could do for protection. And you kind of have to decide for yourself, how paranoid do I want to be? Do I have to do 12 things? Do I need to do 3 things? You got to kind of weigh that out based on how important your data is and everything else. Okay? Most important thing is don't try to write your own. Okay? A lot of people I've seen that think they can write their own cryptography algorithms. There's probably very few people in the world that can. If you're one of them that's in here, good for you. I still wouldn't try it. I mean, there's a lot of people that think they can, they can't. So these algorithms have been a long time. They've been tested. They've been proven. The .NET implementations have been used for a long time. So if you take nothing else away from this, don't try to write your own cryptography. The stuff is solid, and if you know how to use it properly, it's going to do what you're going to want it to do rather than try to do it on your own. Does that make sense? Okay, so we're going to start out with hashing and how hash functions work. So a hash function is a one-way function, so it's easy to compute in one direction, and I put significantly harder because I hate the word impossible when it comes to computers. So really difficult to go in reverse. Okay? So the idea is it's something that's fast. It's going to take, so I gave an example of some data here on the left-hand side. It's going to take that data, and it's going to compute a hash, and it gives me a fixed length string on the right side that represents what that data looks like. Okay? I like the term that it's a data fingerprint. So this hash on the right represents the data that's on the left-hand side, but it's a lot smaller and it's a fixed size. If I were to make even a single character change in that left-hand string, the actual hash function would be very different. Okay? And again, when we talk about using hash functions, I'm going to show you examples of it's okay if people see the data that I'm talking about, I just don't want them to tamper with it. So this is going to be when I want integrity. That's when I'm going to use a hash function. And I'll talk a little bit about being careful when you have a limited value range as we show some examples. So there's an abstract base class in .NET called hash algorithm. That's where all the derived classes are that support, and there's a lot of different algorithms available. I'm going to show you a couple different algorithms as we go. MD5 has been broken, so don't use that. Primarily, I use the highest level SHA algorithm, so the secured hash algorithm. But I'll show you some different examples in here. And there's also keyed hash algorithms, which just means not only is it going to compute a hash, it's going to use a key as input as well. I'm going to show you in certain instances why you want to do that. Okay? So let's take a look at some simple hash functions. So we've got a web page here. I'm just going to take some data. In this case, I've got this string. And if I were to run this, it's just going to compute a hash. So it's going to spit out this hash value. So if we look at what the code looks like, I'll spend a little bit of more time on this just because all of the cryptography is going to look pretty similar to this. So I want to spend time the first time and then I won't throughout the rest. But in this case, I'm going to use SHA-1 managed. So that's the hash algorithm I'm going to use just to make this simple to start. And I've got plain text string. Unfortunately, although you usually have strings in .NET, all the cryptography algorithms deal with byte arrays. Okay, so the first hurdle we have to fight is we can take it out of a string and get it into a byte array. There's lots of ways to do this. I'm going to show UTF-8 encoding is a pretty common encoding that people will use. So I'm going to use UTF-8 encoding, and I just say I want to get the bytes for that plain text string. So all that has done is it's taken my string and put it into a byte array. The reason I mentioned the encoding stuff is later on when you start talking to partners or sending data back and forth or dealing with other people or other systems, how you encode that. If you encode that differently than your partner does, you're going to run into some problems. Okay? UTF-8, again, would be a pretty common one to use. So now that I've taken the string, converted it into a byte array, this hash algorithm has a compute hash function. All that's going to do is actually run the hash function against the data and return me another byte array. So that's actually the hash value for that given string. There's lots of ways that I can choose to display this. So again, it's a byte array. That's not terribly useful to me as far as displaying or passing it to anybody. So I want to convert it back into a string. And there's multiple ways to do this. There's a bit converter that you can use, and you'll see. I'm going to show you a couple different ways as we go through this particular session. You can kind of choose which one makes sense for you. I'll show you why this is useful to me later. But this bit converter will take that byte array, and it takes each byte and gets its hex representation. And I just strip out all the dashes, so it just becomes a string, basically, of hex values that represent that hash. And then I display it. So now that it's a string, I can do a simple display. So that's pretty straightforward to use. Now I'm going to start talking about why would you want to use hashing and some of that stuff. Are there any questions before we go any further about any of the basics? Okay. So where would you want to use something like this? I like something called tamper-proof query strings. So the idea is I was working on a website, and this is pretty typical. I looked at the URL, and it had customer number on the URL, right? Well, everybody knows if you're using SQL Server databases, those are auto-increment. So I said, well, what would happen if I went up and changed my customer to somebody else's? And I did, and I can see it, but the other customer's data, which is obviously a problem, right? So the idea is it doesn't really concern me that much that the customer number is on the URL. It's not something I felt I should hide, but I definitely don't want you to be able to change the URL and see someone else's data. So the idea with this is we're going to use hashing to make this be tamper-proof query strings. So in other words, they could try to change the value of customer number, but if they did, I'd be able to detect that and I'd be able to reject it so they can't see another customer's data. Okay? So the idea is I'm going to take whatever query string I want. So I've got my link, I've got that query string with a customer number. I'm going to compute a hash of that customer number. I'm going to append that hash value onto the URL. That way when the next page gets it, it can look and say, I see the query string. I'll compute the hash. And if it doesn't match the one that was sent, then it can complain. Okay? And again, this has a lot of good uses within websites just because you don't want people tampering with your query strings. I'm going to also show you why you want to use keyed for this. So let's start with a web page that just, so this one has a hyperlink on it. And I follow the hyperlink. Try to focus in at the top here. You can see I've got a query string A1, B2, C3. And if you look, I've also appended, the reason I did that bit converter and the hex is I knew I wanted to append it to a URL, so I wanted it to be safe characters for a URL, so I didn't have to worry about encoding it or anything. So the 1, 2, 3 stuff would have been there before, but this hash is the important part that's going to keep it from other people tampering with it. So we'll look what that code looks like. So obviously now if I want to use this technique, I don't have to use this all over my site. Only particular pages I might care, right? If I don't show customer number on some of them, if they're product IDs, I don't care if you go spelunking around and find another product of mine. I just don't want you to see other customers' data. But any place I want to use it, I'm just going to call this hash query string. So if you see, I used to have just a normal hyperlink. Now I've got to actually construct the hyperlink, right? I've got to be able to compute that hash value. So what I do is I take the original query string I wanted, and I call this hash query string. And all this does is it says I'm going to take whatever the original query string was. I'm going to tack on a new name for my query string. That was that QTP val. And then I'm going to compute a hash like I did before. So let's go to this. This will look very similar to what we had before. I do my encoding. One thing you'll notice here, I'm using a keyed hash algorithm, and that'll become important in a minute when we talk about how someone's going to attack this. So I have a key that I'm reading from my web config. That key is part of the input. So not only is it hashing the string, it's taking this key value as well. And then it computes the hash like it did before, and then it converts that byte array back into hex for me. So that's how I set up the actual query string to go. Okay? The receiving page will, in this case, I chose, if you look, I'm not doing anything special here. How many people in here, by the way, are web developers? I have an idea, or ASP.NET developers. Okay, if you've seen the base page concept before, I just created a base page, and the idea is that I can consolidate all of my code in one place. So this would allow me, if I wanted to, every query string on my site could have this type of support. And you notice, if you use forms authentication, your login page wouldn't have the hash. So you've got to be a little careful where you want to do this. So the idea now, the receiver is going to validate that query string. So the first thing it does is it says, if there's no query string provided here, there's nothing to do, right? Go ahead and return. Otherwise, I'm going to trim off the query string. I'm going to take it. I'm going to make sure that you actually sent a hash value. So I'm going to pull the hash value that was on the URL. I take the query string I just had, and I'm going to compute the hash of it. So I'm computing the hash of what I say the query string is now, compared to what it says on the URL. And these two better match, or we have a problem. Okay? So if I go back and show you a couple things, if I tried to cheat, let's say I changed that A value to 2, it's going to blow up. By the way, again, this is a demo where you'd never see a page like this in production for me. If you haven't heard of this before, there's actually a setting called deployment retail equals true. If you drop that in your machine config on your servers, it'll never show a page like this. And it also makes sure you're never running debug that you don't have tracing on. So I just do that on all my production servers. So, but for your benefit, you can see that. Yep, so there's a tag called custom error. The reason I like the deployment retail equals true is web developers forget to set their tags correctly. And it handles the tracing, the debugging, and this all at the same time. And then what this will do, it'll use your custom error setting and show, yeah, so. But anyway, so this shows the hash value and says, that's not right, something's wrong. If I go back again and I say, well, let's say I play around with this hash, again, it's not going to match. Maybe the guy thinks I'm really not that bright. And if I just take it off, maybe it'll work. If I do that, then I can say there's no hash that was sent. So I've got protection around all those different things. So I feel pretty good about this. It's important, though, that I use the key. So let's go back to, we're going to look at the tamper-proofing code again. It's important that I use the keyed hash algorithm, because if you start to think like an attacker, whatever you're going to do for security, act like you're the person attacking you, and what would you do? So what I would do if I came to a site and I saw that hash value on the end of your URL, there aren't that many different hash algorithms. I'm going to figure out what query string I want. I'm going to compute my own hash, and I'm going to stick it on there, and that would work. And I'll show you how that would work if we did it the other way. So let me go back and just use a normal hash algorithm here. So what I would do is I would go look at this page. I would come up here and see that hash value. Well, let's say I want to use the value a equals 2. So I would go write a little page myself. We'll just call it hack tamper-proof. I know what I want for a value. This is the query string I want to be able to send. I know how to compute hash algorithms just like you do, right? So I can guess it's going to be SHA-1. That's pretty common. I'll compute that hash and I'll get a value back. So let's go back in here. I'll run this. This is the hash value if I want to use a equals 2. So I would just copy that. I would go back. I would change that to be a 2. And then I would change that hash value to be what I want it to be. And voila, I just beat all of your stuff, right? So again, thinking like an attacker would, they're going to probably figure out that's a hash value because you're doing integrity on your query string. But if I were to turn around and make some guesses, so I took one more step on this and said, well, rather than using a normal algorithm, I'm going to use this keyed one. So what that did is it's made it, I put in one more hurdle for my attacker. Now, not only did they have to know the algorithm I'm using, the encoding I'm using, they have to somehow get a hold of this key. So unless they can get access to my web config, they wouldn't be able to do that attack. And it's a lot harder to do that than it is to just run the site and figure out a way to circumvent that. That make sense? Again, right now I'm storing that key straight in the web config. I'm going to show you later how you'd encrypt that again to make it just that much more difficult. So that's tamper-proof query strings. Another thing people use hashing for a lot is hash passwords. So years ago, folks that were doing Unix said, we want to store people's passwords, right? But rather than encrypt it and have to keep a key around, they said, let's come up with a better idea. So somebody said, why don't we take whatever their password is, we'll hash it, we'll store that hash in the password file. Then when you come back, we're not going to decrypt it because you can't go back with a hash, but whatever they type as their password, you'll hash it, and then you just compare the two. And if it's the right password, those two hashes would match. Okay, so they did that. The problem was that they got a little overconfident, and they said, that's really cool. We know nobody can break a hash function, so we're going to let the password file be visible. So if you've used Unix before, years ago, there was an etc password file that anybody on the system could just go read. Because they said, that's fine. Nobody can break hashing, so we're okay. Well, the problem was everybody picked passwords that were in the dictionary. So years ago, I did some research when I was at university, and it was like 75% years ago were actually dictionary words. So what an attacker will do is they'll, again, guess the hash algorithm. They'll take an online dictionary. They'll hash every word in the dictionary. And then they'll go look at what it says in the password file and compare and say, Apple is this hash value. All these people have Apple. So now they can get into all those people's accounts. And that's what happened. So I'll show you how that works. So again, I'm going to show you here how you could do the attack part of it. So I've got this password sitting in the etc password file. There it is. It's hashed, right? I'm not going to try to reverse the hash. I know that's not going to be effective. However, I can take a list of all the words I think it might be. So in the past, when I did this for security research, it was the dictionary, it was your user ID, it was your user ID reversed. They used to have a Unix thing called finger, where you could finger an ID and it would say, it'd give their profile. You'd go in there and take every word out because their wife's name is in there, their dog's name is in there. You'd do that forward and reverse, and you'd get an amazing amount of passwords that you would hit just by doing those things. So the idea here is I'm just going to take a couple example words. I think it might be one of these 3 words. So I compute the hash of those words, and then I just end up comparing to the hash that I already see, and that's how I could break the hashing. So again, the people thought they had a great idea. The hashing was a good idea. Making it read-only, or readable, not such a good idea, right? And they ended up having these hashing attacks, or dictionary attacks, excuse me. So they came back and said, well, what could we do to make this harder? So somebody came up with, have you heard of salted passwords before? So the idea is instead of just taking a hash and putting that in there, they said, we want to defeat dictionary attacks. That's what they were specifically trying to do. So they said, for each password we store in the file, we're going to generate some extra secret, and they called it salt. Then when they compute your hash, they take your salt and your password together and compute the hash value. They said, okay, now we'll store the salt in that file too. Okay, because they need to store that. They need to know for your user ID, they need to know what the salt was. The problem was now all they've done is they've made it hard for me to do a dictionary attack. Right? If I want to do a dictionary attack against this file, I have to now compute the hash of a full dictionary with a particular salt value. So I have to do that for every user. So attacking the entire file just got more difficult for me. However, it didn't get any more difficult to attack a single user ID. So what they did is they looked in there for things like admin, administrator, super user, all those names that they thought would be a privileged account. Now they go take the salt out, they'll compute the dictionary with that particular user's salt value, and they could do the attack just like they did before. So if the person had a bad password, this didn't help. So it stopped you from breaking into a lot of accounts, but it didn't protect an individual account. Does that make sense? So I'll show you briefly what the salting looks like. Again, you have access to the code, so I won't spend a lot of time on it. But you'll generate some random salt. And if we look at this, we'll talk about this a little later too. Whenever you're doing cryptography, random isn't random, right? I mean, there's normal ways to get a random number that aren't really that random. If you need to use what's called a cryptographically strong random number generator, and that's this one. The random number generator crypto service provider is the best for .NET that you're going to get to do a random number. So all this does is it creates a random number of bytes. So I've computed this salt, and then when I compute the hash, all I do is I compute the hash with not only your data, but also with the salt. Okay? That's how they do salted passwords. Once they figured out that, gee, people are still breaking into the admin accounts and stuff, they said we need to do something else. So in cryptography, something else means put some more random data in. Okay? So they started doing what they called entropy, which is just another piece of random data. So I generated another piece, but the difference is, to me, this is like a key. I'm going to keep this secret. I'm not going to shove it in the password file. So now if you attack somebody, you have to know hash algorithm, how they encoded it, their salt, and then you somehow have to break into my code and figure out what that entropy is. So if you look at modern systems that do password hashing like this, and they all do password hashing, they do all of these kind of techniques and more to make it difficult for people to break in. Okay? But just wanted to give you an example of where hashing is useful. Some places they do hashing in .NET. So if you're familiar with ViewState, if you're a web forms programmer, I happen to have a web forms example here. I just want to show you a practical place in ASP.NET where they protect you by using hashing. And one of them is this ViewState Mac. So let me go hit a page here. I'm going to start up Fiddler. How many people use Fiddler in here, just so I have an idea? Quite a few. Okay. So Fiddler watches traffic between my browser and my server. So what I'm doing now is I'm going to pull up a page and hit a submit. And one of the cool things about Fiddler is you can actually modify requests. So these are what attackers would do. They're going to take this, they're going to drag it over here. And that was what I just posted. And here's the value of the view state that was just posted. Okay. I can go in here and play with this. So if I go back, I'll show you what the code looks like quick. I'm storing a value in view state. So I stored the value of 1 in view state. That got sent down to the client. Using Fiddler now, I can drag this request over to the composer, and I can make some modifications to it. So let me change that to that, from B to C. I'm going to do an execute on it. If I go back and look what the server said, you can see it posted back the value 2 instead of 1. So by manipulating view state on the client, I was able to make changes to things that you store in there that you think are safe. I'm manipulating on the client and sending back to the server, okay? Which could affect how all of your controls work. So if you go into your web config, there's a setting that view state mac equal to true. If I were to set that to true now and do the same thing, it's appending a hash on just like what we've been talking about. So not only does it send the view state data, it sends a hash of that. So by the time it gets to the client, if anybody makes any changes to it and posts it back, ASP.NET will blow up and say somebody played with that view state and it's not valid anymore. Okay? So if you've got the view state is invalid, that kind of message before on a server, that's the mechanism, and that just shows how they're taking advantage of hashing to make sure that your data is not being manipulated on the client. Okay. So any questions on hashing before we move into some of the other encryption? Okay. So these are the terms we're going to use for the encrypting part. So the first one, these are just standard cryptography terms. Plain text is your original data. Encryption is your process of obscuring that data. Ciphertext is the stuff that's encrypted. Decryption is your process to recover your original data. And then the cipher is the actual algorithm we're going to use to do this encryption and decryption. So those are the terms as we start walking through some of the rest. So the first one we're going to talk about is symmetric algorithm. So when most people think about cryptography, this is usually what they think of first, a symmetric algorithm. And the idea is, I don't know how viewable that is here, so I'll try to point it out, but I've got my plain text, so I've got whatever I want to encrypt. I run an encryption process using a secret key. I send that data, or I store it, whatever. The next person who wants it's going to decrypt it, but they also will use the same key, and then they'll get the plain text back. So as you see, the idea with the secret key is you got to keep it secret, right? I mean, it's the same key for encryption and decryption, so you have to be careful about that key. So the bad news is key distribution with symmetric is difficult, right? I mean, if I have a new trading partner, I have to figure out a way to get this secret key to them in a way that other people don't see it. And the primary attack people are going to use for this is they're going to try every possible secret key. I mean, they can't crack the algorithms because they're too well done as far as how the algorithms work. So they just say, however big that key is, I'm going to try every value of that key until I get lucky and one of them works. So that's the way people will attack this. There's a lot of different symmetric algorithms. I'm going to focus on the first one. It's called Randall. It's AES encryption. So in the United States, that's our government-sponsored, what they want us to use for encryption. And that's one of the better algorithms that's available. So that's the one I'm going to show you here. So we'll show it running first. I've got some plain text here. I'll just put in DevWeek 2014. I'll do some encryption. This is the encrypted ciphertext. There's an initialization vector that we'll talk about here in a minute. And then when I do the decrypt, I get back to what I had. Okay? So how do the symmetric ones work? They use what's called a block cipher. So they're going to take whatever your text is, break it into blocks. It's going to encrypt it a block at a time. Okay? Once you start doing blocks, a couple things come up. The first is padding. So I'm going to talk, the one I'm going to show you is a 256-bit block size. If your data doesn't happen to be exactly 256 bits, you need to fill the rest of it with some sort of padding. So there's 3 different kinds of padding that you can use. One is zeros. So whatever is not filled in just gets filled in with zeros. The next one, the PKC27, just fills it with however many bits are empty. So in other words, if I have 2 bits empty, it puts the value 2 into each as it pads. And then the last one that you actually want to use is the ISO 10126. It puts random stuff in to do the padding. So it knows where the last packet ends, and it fills the rest with just some random stuff. And I'll show you why you want to use that one in a minute. Okay? The next thing the block ciphers do is they have a mode. And the mode of ECB just says split up the data into blocks. So I take the first block, I encrypt it. Then I take the second block, I encrypt it. It just does each block on its own. To add a little bit more randomness, they created what's called the CBC mode, which is I'm going to encrypt the first block, and I'm going to use that encrypted data as input for some randomness into the second block that it does encryption with. As soon as you start doing that, then the question is, what are you supposed to use for random data for the first block? That's what the initialization vector is. So the initialization vector is just some random data that's seed input into that first encryption if you're using CBC mode. Okay? I'm not. This always baffles me when I read this and saw this, but the initialization vector does not need to be secret. Okay? They can see that. It doesn't matter for the algorithms that somebody sees that random data. But you're never supposed to reuse an initialization vector. That's what's important with those. So it'll get generated each time. Just never reuse the same value, or somebody can see patterns and break into your stuff. Okay? So again, when we show you for real, use the ISO, use the CBC. You'll get a different initialization vector every time. Just use the different one every time, and send them both, and you'll be good. Okay? So let's look at what the code looks like. So when I go to encrypt, the first thing I'm going to do is create my cipher. So let's look at what this looks like. So I'm using the Randall manage class. And again, in cryptography, this manage just means the actual algorithm is written in .NET code. Okay? There's also a version of Randall that's not managed. So in other words, there's the crypto providers that you get from Windows. That would just be a shell to get to the underlying Windows crypto. So you can use either one. I happen to use the managed.NET version. I'm going to use a key size of 256, a block size. Those are the largest that are available for AES. We'll talk about key size choices later. I'm going to use the 2 choices I recommended you use, the ISO and the CBC. And then I've got a conversion algorithm that will take my byte array and convert it into hex. So when I actually do the cryptography, now I've got my Randall manage class with all my key stuff that I need. I'm just displaying that initialization vector on the screen. Again, if I'm going to send this to say I send this to you, I've got to send you the cipher data and that initialization vector for you to be able to do the decrypt. So that's why I'm showing it on the screen so you can see what it is. I create my encryptor. Just like I did before, I need to take my string, which is in the text box. I need to convert it into a byte array. So I'm doing the same thing I did with hashing. I'm just using UTF-8. So that converts it into a byte array. So now I have a byte array that represents the data that you want to encrypt. Then I call this transform final block. That's what does the actual encryption. Now I've got the encrypted text. And again, in this case, I'm showing you another way to do a byte to string. Base 64 is a pretty common encoding that people use as well. So you can use the base 64 to convert it into text. Okay? And the decryption ends up being the opposite. I take the initialization vector. I know that that's base 64 encoded, so I reverse that. I create the decryptor. I get the ciphertext back into a byte array, and I do the transform final block, which does the decryption. Okay? So again, the key here is that it's going to use the same secret key. So if I run this, we'll show what the values look like again. I'll just use test. Now you watch, each time I'm doing encryption, because I chose to use the more secure modes, you'll notice that ciphertext here changes every time. If I were to go use the worst modes, I'll call them, I often wonder why they even provide them when they're not that good. But I'll turn these on. Probably for compatibility, I suppose, if somebody else doesn't have that in theirs. If I run that again, and what you'll notice, watch the ciphertext. Every single time I encrypt, because I'm not using the CBC and I'm not using the ISO, that value is the same every single time. The ciphertext is. So the bad news with that, I mean, in general, that might not hurt you. But let's say all I ever send you is yes or no, buy or sell, whatever. If those are the only two values I ever do, it doesn't take you very long. You don't know what this means, but you can watch how I react. You'll figure out these are yes and no pretty quickly, and they're going to see that value every single time. So it's just not a wise choice. You want it to look different every single time, even if the data happens to be the same. Okay, so that's why you want to use those two. Okay?
On that example, the IV isn't being used.
Yeah, in that example, it happens to always make a random IV, but yeah, the IV doesn't get used because of this mode right here. Yep, so you wouldn't have to transmit it. Any other questions on symmetric? So again, symmetric is cool, it's really fast. The problem is distributing keys can really be painful, keeping that key secret. Yes? So the question is, what's the default on these? I honestly don't know. I always specifically set, so I'm not sure. Yeah, I mean, again, I think the only reason they must have these is because other people who use AES or Raindoll have the ability to set some of these things. So maybe if a partner says, we don't know what we're doing and you have to do it this way, it would be for compatibility. I would hope that they would do these as the defaults, but maybe this other one had been the historic. I'm not sure. The padding mode right here? Yeah, that's the one that puts random bytes in to fill the padding of a block that doesn't fit the block size. It'll just generate, I mean, it knows where it knows where it needs to put padding, so it decides then to pad that out. It'll generate random bytes to put in there. How does it know where the end of that? Something in the algorithm. I haven't figured that out yet. They must have a marker where they know the end of that padding is, and they know that the rest of this is padding, but they don't want it to be the same.
I mean, like, from what I know, when you crypt something that has padding with zeros,
Yep.
And if you're using an invalid key, you will get padding invalid.
Okay.
Padding
Yep.
doesn't match. But that's for zeros. I don't have.
Yeah.
What you get, if you use an invalid key, would you get what kind of error would you get? An exception or just gibberish?
So the question would, if somebody,
This time you get a wrong text.
Yep.
Something
somebody
that you're not
got
using.
modified.
Yeah, something that got.
Yep.
Would you get an exception? Or
Yeah, .NET will throw an exception if that change data was in your padding. I think they would probably still complain that something was different in there because the decryption isn't going to work,
Yeah, okay.
if that makes sense. Whether they differentiate that it was in the padding or somewhere else, I don't know, but they would throw an exception basically saying that the decryption didn't work because it wasn't correct. Any other questions on this for symmetric? I'll talk a little bit about crypto streams. So if you do a lot of streaming, crypto streams can be useful. So if I have an example of, I want to do some encryption, so I want to take some data, I want to encode it, and then I want to write it out to this file. So in this case, I'm going to create my cipher the same. For this example, I did this, and I'll show you why, because I want to get the same value all the time. But using streams makes this a little easier than if I had to do this manually. So what I can do is I can create my file stream. So this is normally how you would write out to a disk file. They also have a stream to do the base 64 transforming. And then I'm going to create my normal cipher like I would. I can attach streams on top of each other so that in the end, so I say I want to put base 64 on top of the cipher file. So in other words, I'm going to write it to the file, but before I write it, I need to base 64 encode it. That's what this line's doing. And then on top of that, I want to put the encryption. So now all I have to do all of that work if I'm going to write a lot of encrypted data, I can now just say write to that crypto stream, and it's going to do all three of those things. It's going to encrypt it, base64 encode it, and write it out to the file. So if you happen to do a lot of stream work and you want to patch encryption in there, and let's say I'm going to write this hundreds of times, the crypto streaming approach can make sense. I just wanted to show you an example of how you can do streaming like that, okay? Rather than have to do each step manually. Okay, so there's some places where this is used again in ASP.NET, and I'll show you the view state example again. So the idea is, again, lots of different places. Symmetric is actually used within .NET itself, and this is just one relatively easy example to show. So if you haven't heard this before, storing secret data in your view state that goes to the client, generally not a good idea, and I'll show you why. So if I store secret data into my view state, and I go look at what this page looks like, I can just do a view source. I can take that view state, and there's actually a tool, Fritz Onion, who now is one of the Pluralsight founders, wrote this tool years ago to decrypt, or I shouldn't say decrypt, to decode what's in view state. So people were having issues with view state. They couldn't figure out how view state actually got stored. This tool lets you do the decoding. And if you look, that's the bad thing, right? I mean, it's on the client. People can actually see that data. So storing things in there that you want to have be secret, generally not a good idea. In ASP.NET, they realized that some people were going to do that, so they set this encryption, view state encryption mode. So I have it to never right now. I can set it to on or auto, and then it will actually use symmetric encryption when it stores that stuff on the client. Okay? That happens to be the default, and the reason I know is because I have a production web farm. If you have a production web farm and you have people crossing your web servers, so we were an early adopter of .NET, so when 1.0 came out, put it in our web farm. As soon as you did a post back, you got a view state's invalid. They'd gone to one of the other production servers, and the view state key, so it has to have a key, right? It's using symmetric encryption. ASP.NET generates its own key per server, so if you go to a different server, the keys don't match. So the encryption was good, but the problem was it has to store that key. It stores it per server. So to do that, you have to actually make sure you have the same symmetric key across all of your servers to take advantage of this. So just be aware if you use this feature, you've got to make sure that key is the same if you allow them to cross your web servers in a production farm. Okay? So any questions on symmetric or how that works before we move on? Okay, next we'll talk about asymmetric. So the idea with asymmetric is it's going to use two complementary keys. So if you've heard of public-private key encryption, that's what asymmetric is. Problem with asymmetric, it's nice because it makes the key distribution issue go away. The problem is it's like 1,000 times slower than symmetric. So that's the drawback of using asymmetric. So what people will often do is they'll use an asymmetric algorithm. They'll create a key to use for symmetric. They'll encrypt that key with asymmetric so they can send that key to their partner. And then for the rest of the conversation, they'll do symmetric. Okay? And that's used in a lot of systems that want to take advantage of both of these. So again, on the picture, the plain text comes in. What's a little goofy when you see it for the first time, when you're going to encrypt data for someone, you're going to use their public key. Okay? So each person that's going to be in this is going to create a set of keys, one public, one private. Obviously, public one is the one they hand out to everybody else. The private one is the one you don't want everybody to see. So when I want to communicate with somebody, I'll say, give me your public key. They give me their public key. I'm going to encrypt using their public key. The reason is the only thing that can decrypt it now is the private key for that pair. So that receiver has their private key. Now they're the only one who can decrypt it. Anybody else who sees it can't do decryption because these two keys go together. Okay? Again, there's a number of different classes that you can use. I'm going to focus on RSA as the algorithm I'm going to use for these examples. if we pull up the page, let's see what it looks like first. Do test again. I just display the keys. We'll talk about key generation in a minute, but this is the encrypted, the ciphertext. You see when you decrypt, you get back to where you started, which is a good thing. So let's look how this one works. There's a lot of different places that I can store my RSA keys. So when you see all the comments I have in here, I did that because you have a lot of different places you could store it, and I wanted to show you how you would take out of different places. You can store the key in your Windows crypto service provider area. I mean, it'll store public-private keys for you. So that's what this top part is. That wouldn't work real well for demos, right? If I gave it to you, that's not going to work. So I focused instead on all these demos are going to use XML. So I created a set of keys. And if you look in here, I've got this RSA create script. It's got all the different functions you need to run to be able to create RSA keys. So the first one I would run, if I ran this at a command prompt, this will create for me a public-private key pair named RJB RSA keys. Then I can export it. So in this case, I can export it so the XML has both my public and my private key, or so it just has my public, depending on who I want to give it to. So all the examples I have, I already created my keys, and I've exported it into XML, and I've got two different ones, the one with both keys and the one with just the public keys. Okay? So if I go back. So in this case, this has both of my keys. So I create my cipher again, which is just this RSA crypto service provider. I need to put the keys I want to use into it, so I just tell it get it from XML based on those keys I have stored above. And then I actually do the cipher for the keys. So there I'm just showing what the keys look like on the screen, so you can see what keys I used. When it comes to encryption, it's pretty straightforward. I create my cipher. I do my encoding again, so I have to take my string, convert it into a byte array. I call encrypt, and then I just do the base 64 encoding so I can show it as a string. So that's the encryption process using the asymmetric. And then to do a decrypt, I do the opposite. Okay? So I create the cipher again, I do the decryption. So now I want to show you an example of submitting back and forth. Actually, I'll move to this next one first.
When you're encrypting,
Yes.
how does it know when you're encrypting via the public or the private? Is that what that Boolean false?
So when I specified, so where's my encrypt? In this example, I'm using the same key pair just to do back and forth. Usually, and I'm going to show you an example now where you'd have a partner. So you'd have somebody else's key. You usually see two different keys because you're sending to a partner, if that makes sense. In this case, it knows when it does the encryption here, it's going to use my private key by default. And then when it does the decryption, it's going to use the public key of that XML string, whichever one that was. Okay. So where would I use this? This is a very practical example for me for asymmetric. If I wanted to encrypt, say somebody comes to my site and they have a credit card number, right? As soon as I get that credit card number, I want to encrypt it so nobody can see it. If I use symmetric, that would work, right? But if I use symmetric, I have to store a key somewhere. And I already said, for me, I don't want to store keys on my web servers that sit out on the internet. I believe somebody's going to take that box and be able to read everything on the disk. So the way I can avoid putting that key anywhere, I'll skip using symmetric. I'm going to use asymmetric. And with asymmetric, I generate an RSA key pair. I take the public key. I use that on all of my front-end web servers. The private key I put only on a box inside, behind my firewall. There's only one box that has that private key. So that's the only guy who's going to be able to do any decryption. Okay? It's typical today with vendors we've worked with for secure payments. They actually give us their public key so that nobody in my company can even decrypt it. As soon as I take their public key and encrypt it, I can store it anywhere on my databases. No one in my company could ever see that data. When I send it to the processor, they have the private key, and they're able to get back the credit card number. Does that make sense? So this is pretty typical. industry way to approach it. But so again, I'll store that public key on my web server. I'll even put it right in a string inside my code because I don't care if you see that. That's my public key or someone else's. That private key is going to be stored internally. Again, it's asymmetric, so it's going to be a little slower. It's well worth it for me for the security. And I have an example in here. If you're unsure about the performance impact, just run a test. I mean, I can run a test. This asymmetric runs pretty fast. It's worth me not storing a key on my web servers to use this approach. So let's look at what that would look like. So the same thing, now what I did this time is I decrypted, or I created my key pair and I only exported the public key that I want to use for the encryption. So that's all that's in this XML string. When I go to encrypt now, I say, same thing we did before, creates the crypto provider, it reads that public key out of that string, and then when it does the encryption, that's the only key that's in there, it uses that, it encrypts that data, and then I get back the ciphertext now. So now that I've encrypted it with a public key, I could store it in a database, pass it to my middle tier, whatever I'm going to do with it, send it to a partner. The person with the private key is the only one who can decrypt it after I've done that statement. Okay. So again, now I'm glad that data is secured, so I'll show you, I've got, for this example, let's just run it once. I do the encryption, so there's my ciphertext. Now, let's just say I store it in a database. Anybody could look at the database. It'll be encrypted. That's fine. To simulate an internal system, I've got just another page here. I'll paste that in. He can do the decrypt and get back because in this case, he has the private key. Okay? So here he's got the private key and the public. He converts that from that XML string, does the decryption, and now gets the data back. That make sense? So any questions on asymmetric before I move on? Because the next one's going to be kind of a combination.
So is asymmetric?
How much slower?
Yeah.
They say about an order of magnitude slower than symmetric. So 1,000 times, something like that, worse. Now, in my mind, again, I'll show it to you because I just did this. I'm of the paranoid type. I'm more concerned about security. I'm also a performance guy. I'm going to do a performance talk, so it's not like I don't care about performance. But if I'm unsure, I go in here, I created this performance page. I did it for hashing. I just said I'm going to take every one of the hashing algorithms. I'm going to run 10,000 hashes with it just to see how this performs on my machine. And it's a pretty decent laptop, but your servers should be better. And you can see that we're in the milliseconds for running 10,000, so I don't care. I mean, you'd have to try it out for yourself. Try the symmetric, the asymmetric, see how much slower it is. But
there was a significant amount of data passing.
yes. So the data, the important part for that example was I'm talking just a credit card number. That makes sense. If you have volumes of data, what people will do instead is they'll do make a symmetric key, encrypt it using the asymmetric, use the symmetric to do the encryption. That's what SSL, all those algorithms use. They have the asymmetric for the server has their public key. You do the encryption stuff, but while the real encryption of all your data, that's all symmetric. So you kind of balance the two of them. In this case, I didn't bother with the complexity to do both because the asymmetric happened to be fast enough because the data was small. If that makes sense. Yes?
Just out of curiosity, this question is, it's not to do with, I've read that to make a public-private key pair, the algorithm basically is you take a very, very, very large prime number and split it into two. But the way it is split is you cannot reduce one key from from the public to private or private to public. Any thoughts what happens in the background? It's just a curiosity.
I've got some very good examples at the end for resources. So the question was just, how are the keys created? They're based on prime numbers. How do they split them up?
Go from one key to another.
Yeah, so
essentially the same number which they have split from.
yeah, so the security part of it is that. How do they make it so that when you have a public key, you can't deduce the private key?
Yeah.
And so look at the end, I've got some resources that go into way more detail than I could follow for how that stuff worked for primes and such. But they explain why you can't deduce the keys. Because The whole crux of asymmetric
It's
is
essentially
broken.
the same number,
If yeah.
Broken into two.
If you could, the fact that computers are, it's hard for computers today to compute large prime numbers.
Yes.
That's what makes so someday when they make a computer where that's really fast, all the asymmetric is toast. Because all these keys will be public, you'll be able to figure out everybody's private key. That is what it hinges on, but I've got some examples at the end that'll go into some of that. Or some resource, I should say. Yeah.
Are you aware of any problems out of this out of good practices? Are you aware of any problems if you reuse the class for the cipher? So are you allowed to, sort of good practice, to reuse cipher? So when I noticed that the most sign was being used, not actually doing the cipher itself, but creating the actual class. So every time the initialization took a long time. So
Yep.
Sometimes what I did was, okay, reuse it.
Yep.
Every time. I don't know, I mean.
So the question is, if I were to go to, let's look at the asymmetric one again.
Creating the cipher every time.
I happen to be. So the question is really, is it evil to cache this or somehow reuse that over and over? That shouldn't make any difference. So like you said, if you've done the performance analysis, creating the cipher can take a while. You could cache that or store that. It's not going to affect the security of the algorithm to reuse that cipher because there's nothing other than the keys that goes into the actual encryption and decryption process, so you'd be fine. Okay, so let's talk about digital signatures. The idea with digital signatures is I want to provide integrity. So if you send me something, I want to know that it hasn't been tampered with and that later on you can't claim it didn't come from me, right? That's why I care about digital signatures. So the idea is you're going to take a message, you run a hash on the message, that's going to give you the integrity, right? You can tell if it's been tampered with if the hash is different. Then you're going to use the public-private key. You're going to sign that hash. And again, when we're talking about performance, they don't sign the message because that could be big and expensive. The hash is a fixed size. If they sign the hash, that's good enough. So the idea is you're going to hash it, you're going to sign it, and then on the other end, they can look and say it hasn't been tampered with, and I know it came from you. So this is going to be kind of when we get into this demo, the mother of all the rest of the demos. It's got hashing, it's got the asymmetric. It reverses some of the keys, so your question on which key did it use earlier comes into play here too, as far as which one I'm going to use, it knows to get the reverse of that one. So on the screen here, I'm going to walk through the conceptual first. I'm going to take some plain text data. I'm going to, and in my example here, I'm actually doing encryption too. Okay, I chose to throw in encryption as well. Digital signatures don't require this step, but if I'm sending you something, I may want it to be encrypted as well. So I'm going to encrypt this data using your public key. So I'll pick you as the victim. You give me your public key, and I'm going to send you some stuff. I'm going to take your public key to do the encryption. That's what we saw before. Once I do that, only he can decrypt the data. I'm going to take that encrypted data, compute a hash of it, so that I know it won't be tampered with. When I get that hash, I'm going to take my private key. They call it an encryption, but I'm going to sign that hash with my private key. The reason I do that is you can use my public key as the reverse to prove that I'm the only one who could have signed it. That's what gives you the non-repudiation. Okay? So that's kind of the flow. I'm going to send then the ciphertext and the signature to the other person, and they can reverse and prove that that all worked. Does that make sense conceptual? Because then I'm going to start showing the code for how that would perform. Okay. So if we pull this up, we'll do just a quick example. I'm going to click, I passed a secret. So if we look up here, I sent to another, in this example, I just sent it to another web page. I could transmit this however I want. But I passed the secret, that's the ciphertext. And then at the end, I passed the signature, which is the hash that I've signed. Okay? So let's look at the code for this. As the sender, I've got two different sets of keys here again. I've got the public key from my receiver, as an XML string in this case. I've got my own private and public key pair. I'm going to create a cipher using my keys, basically. That's the sender cipher. And I'm going to create a receiver cipher using their public key. So now I've got two RSA ciphers set up using two different keys. Here's my super secret credit card number that I want to send. I'm going to do the encoding I always have to do to get it to be a byte array. I'm going to do then the encryption process. So I've taken the receiver cipher. That's what is using their public key, and I'm doing the encryption process. Okay? So I took the data, I made it into a byte array. I've now encrypted it using the receiver's public key so that only their private will undo it. That's going to be the encryption part. Then I'm going to create a hash. I'm going to compute a hash of the encrypted data, right? Because that's what I'm going to send. I'm going to compute the hash, and then there's some built-in classes to make the signature code a little simpler. So what I'm doing is I'm using in this case, my key pair to do the signature of the hash. Okay? So when I create that signature, it's now taken my private key and signed that hash value. And then I just convert those both into strings so I can send them both, and then I put it on the URL. Okay? So now it's encrypted, so when you receive it, you know nobody else saw it because it was encrypted. You can check the hash so you know that it hasn't been tampered with, and you know that it's from me, right? That's the digital signature. The only thing I could possibly do is later on, if you came and said you signed this, I could say somebody stole my private key, and then you're going to be in court debating if that's true. And if it is, then all my other signatures are invalid. I mean, that's really the only recourse, because from the technology standpoint, you know I'm the one who signed this. So that's the sender. If we look at the receiver, this is going to be very much the reverse. Some of this is just the web code, so I won't spend a lot of time on it. But I'm going to pull the secret and the signature off the query string. And then I'm going to do a bunch of the reverses. So I'm going to take the ciphertext. Here I'm going to get the hash. So I'm going to recompute. I took the encrypted data. I'm going to recompute the hash on the receiving side just so I can make sure that these hashes match. And again, they've got some code here to make the signature validation easier. You have my public key. So you can check that the hash is okay, nothing's been modified. And you can prove that I was the one who signed it because my public key is the only one that can reverse that signature and say that it's from me. And if the signature doesn't work, I throw an exception. Otherwise, I've got the ciphertext I want. I'm going to decrypt it using the receiver's private key, and then I've got the data back and everybody's happy. Okay? So a lot of stuff happening. I mean, if you step back and look, there's really not that much code here to make all of that stuff occur, to get encryption, integrity, and non-repudiation. It's pretty straightforward using the .NET stuff. That make sense? So that's digital signatures. Now we'll talk about protecting config sections. So there's certain sections of a web config that you can choose to encrypt. And they've got details. Generally, you can't do the process model, the runtime. But the main thing you want is the app settings, where you store your key value pairs. That's easy to encrypt. There's really two ways to do it. I'm going to show you both ways. I'm going to tell you why one is probably not really that useful for you, but it's easy. And if it works for you, great. So the first one is DPAPI. If you've heard of DPAPI, it's some encryption that's been built into, since Windows Server 2000 and XP. It's something provided by the base Windows system, and it manages its own keys. So you don't need to worry about any of the key storage. It generates a per key, or per server, set of keys to use for encryption and decryption. So you don't get involved in any of the key stuff. You just say, I want to encrypt or decrypt, and Windows knows how to use this key. Okay? It's very easy to use, so I'll show you how to do the actual encryption. So first, let's look at our web config file. So I've been storing, here's a bunch of keys I've been storing throughout these demos. Generally, I feel like somebody can read my web config file on my server, so I don't want to do this in production. That's why I'm going to do the encryption. If you look, there's a protect script.txt I gave you, and here's the line that I want to do the encryption. So I'm just going to say I want to do the app settings in my crypto website, and I'm telling it to use DPAPI. So let me go Go to administrator prompt. I'm going to run that. So I run that on my machine. It's now used whatever keys are on this machine for DPAPI. If I go back to web config, it says it's been modified, and voila, nobody can see that data anymore. So that's good. I'll give you one little caveat to that. So if you look at the physical disk, that's what you see. However, if you think, well, how does ASP.NET work? I want to go pull out that app setting. They decided not to make it hard for developers to pull data out of encrypted web config. They made it transparent. So if I come here, I can just run this. And without doing any extra work, it got the data even though it was encrypted. Great. That's kind of good and that's kind of bad, right? I mean, the bad part of that is any developer can cheat, right? I mean, if you encrypt this, not only a developer, but anybody who could change a web page on my server could run it and say, I want to see what's in that app setting if they know that app setting value, and it'll cough it up to them. So yes, it's good to use this because somebody who can only look at the disk and doesn't know a lot can't see my key. However, it's also got one, it's not perfect either. You can't sleep at night soundly knowing that somebody can't get this, because if they can change your page, they're going to be able to see this. Does that make sense? So let me put that back to what it was. The other problem with this is, I don't know about you, but I have a test stage and a whole bunch of production servers, right? This is a per server key. So I don't want to go to each server and do this for web config. That's just not going to fly. If I only had one server, that might work and it's easy, but probably not realistic for most. So I'm going to go run this again. This was going to do my decrypt. So if I go back, hopefully my web config will be back to the way it was. So I'm going to show you the other technique that you can actually use. And this is using RSA. So you're going to encrypt it, but now you got to manage these key pairs. So the steps are, you generate a key pair, you set up your web config provider to point to that key, you run the encryption using that command tool. So I could do this on my dev server, right? I do that encryption, I export that key pair, I go to each other server, import that key pair, because I have to have them all know these keys, and then all of them can do the same process. Now all of them can auto-decrypt that web config section. So I won't go through all of the work. It's in here in this. I'll show you where it is in the file. It gives you all the steps. Here's how you create keys and give them a name. Here's how you set up your web config to point to that. You can see there's obviously more work to this. Once I have that set up, I can run this command to do the encryption. And if we go back and look at our web config, it's a lot bigger, but that's using RSA. So now this will work across all of my servers in my farm. As long as that server has that key pair imported, it'll be able to auto-decrypt and support the same kind of encryption that I wanted. So this is realistically, if you feel you have to take the step of encrypting your web config so people don't see these secrets, which I think is wise, that's how you would do that in a real production environment. Yes?
So that's like web config. If you've got Windows services, does the same thing work for app config?
So the question is, does this work for app configs? I honestly don't know.
Why would you do it?
I would imagine that there's a similar feature, but I haven't tried to do it for an app config before. I hope so. I mean, I don't see why they would do it just for web and not anywhere else, unless obviously we've got a lot more exposure on public internet than internal. But so let me undo this before I forget to. And then I'm back to where I want to be. So again, just another hurdle. I don't want people to be able to look at the disk and see my stuff. That's how you can approach it. Talk a little bit about key size and storage. So when we talked about symmetric and asymmetric, the larger the key size you choose, the slower things are going to be. So if I picked a symmetric like AES, if I picked 128-bit encryption, it's not just linear, 128-bit versus 256-bit. It's a lot slower. It's also a lot harder for somebody to break. So again, my personal stance, I use the highest key sizes that I can. I've done the testing. The performance impact of it is so small compared to how much more secure it is. I just go to the top end of all the key sizes that are supported for .NET, and that's what I use. If it turns out you've got a strange scenario where running symmetric on this thing is so huge it takes 3 weeks to run, if you can afford to be a little less secure and that fits for you, then do that. Otherwise, use the largest key sizes that you can. One thing you'll notice, the key sizes for symmetric and asymmetric are really different, and that's just how the algorithms work. So it's not, the symmetric is 256 bits, asymmetric RSA would be 4096 would be your top. It doesn't mean that RSA is that much better than the symmetric 256. Those key sizes aren't comparable. But within each algorithm, pick the top end that you can if you're more concerned about security, which hopefully you are, because that's why you're here, right? As far as key storage goes, you can decide where you want to put things. I didn't demo it here, but if I stored a key directly in my code, some people put string whatever equals, here's their key value. That gets embedded inside your assembly when you build it. So anybody who has ILDASM or any of the tools can go run it, and especially if you're kind enough to name it password, they can go in and just search for password off your DLL and find all of your stuff. So storing it in a string probably isn't wise. If you're sure somebody can't get a hold of your assembly, I mean, again, these are decisions you're going to have to make. You can put it in an encrypted section of web config. That's pretty decent for web. I mean, we showed you'd have to have the key pair to be able to do that decryption, or you'd have to be able to change a page on the server. Can people do that? I believe they probably can. It's another hurdle again. I've seen people say, I'm going to split stuff. I'm going to keep part of it in code, part of it in the registry, part of it in the web config. I mean, go as nuts as you would like, or you feel necessary, to make it more difficult for the person to be able to get access to your keys. Okay? Again, I personally, from a key storage standpoint, I've been able so far to say, I just don't store them on my public-facing web servers. I use asymmetric on purpose, so that doesn't affect me. I don't want to store a key because I don't want somebody to get at it. And that was the best answer for our approach. Talk briefly about some other .NET cryptography. So there are some XML encryption classes if you're specifically doing some XML work. There are some around digital certificates. If you have X509 certificates, there are some classes that help you deal with those. There is an enterprise library cryptography block. So as I said, I started .NET when it was still beta before it ever got released. So we were doing our own cryptography using what I've shown you before the cryptography block came out. So if you use, how many people use enterprise library? It's from Microsoft's Patterns and Practices group. They have a cryptography block. I've looked at it. My personal opinion, using the stuff I've shown you already isn't very difficult. That I just as soon not have another layer in there that, I'd rather use what's built in that I know everybody else uses, that's been tested a lot. I would use the enterprise block if I felt it significantly contributed something to my code being easier or more maintainable. I don't think what we're using here is very difficult, so I don't happen to use it. Secure string. So a while back they said, it's bad to have a string that you store in memory because if somebody does a process dump, they could see that string. So they said, let's make a secure string in .NET. So if you store something in a secure string, it's actually encrypted in memory. I said, that's awesome. How cool is that? The problem is to get it out of a text box into a secure string, it goes through a normal string. And so it's still going to be hanging out here in a normal string until garbage collection occurs. When garbage collection occurs, yes, that'll go away and I'll still have my encrypted one. So it's got some uses. I really was disappointed there wasn't a way in .NET to get it out of the text box straight into a secure string. That makes sense. Protected memory and protected data are the same thing. It's a way to store encrypted stuff directly in memory. They just support things other than strings. So again, if this makes sense for you, you're going to store a lot in memory that you need to have secured, you can put it in there and that's fine. Just be aware until that first garbage collection occurs, it probably went through a normal string or some other data type that's still sitting in memory, so you're not totally covered. Okay? So the summary, main thing, don't try to write your own cryptography. I mean, use the stuff that's built in that people have tested. Use hashing when you want to validate integrity. Use symmetric unless you have special needs. So again, symmetric just because it's really fast. use asymmetric if you need digital signatures, or like I do when I'm storing something. I want to encrypt on a web server and I don't want to store a key. I can store my public key there. That works great. Know your threats and choose the proper countermeasures. So again, understand, do I want people to not see this, or do I not want them to tamper with it? That drives whether you use hashing or encryption, whether you're going to do any of the signatures. Think like an attacker too. I mean, I showed you how the hash passwords seemed like such a great idea and nobody would break them. Nobody thought, well, if I did this dictionary attack, until it started happening to people. And they made it more difficult. And that's kind of the constant game of, you think you have something good going, someone's going to figure out a way to get around it. What are you going to do next? Some resources, I do have a course on Pluralsight that goes into more detail on all this. Applied Cryptography is a really good book. It's a little older, by Bruce Schneier, but it covers a lot of good stuff. These other two, when you were asking about the mathematical stuff, about primes and stuff, those two go into a lot of detail about the prime numbers and how they get generated and why they're difficult and why you can't get the reverse pair. The bottom two are kind of entertaining just because they talk about how they're more historical books about how people have used cryptography, how the Allies broke the World War II codes of the Japanese and the Germans, that kind of, so some good historical, what people thought was safe, what wasn't safe, how did they crack algorithms, that kind of stuff, if you want to read on any of that. My blog, my email, my Twitter, we've got a couple more minutes for questions. He asked me to tell you there is an app for the conference, if you didn't know that, and on there you can go to the session and you can do an evaluation. So he and I would both appreciate it if you could fill out an eval for us. I've got some month-long trial cards for Pluralsight. If you're not a subscriber, you can come and get one. And otherwise, take questions, or you can be early to lunch, whichever you want.
So these samples you provided?
Yeah, so the samples, I haven't been able to verify yet, but you each got a USB. They told me those are going to be on that USB. And so all the code stuff I showed you is already on there. And if it's not, go ahead and contact me. Okay. Anything else? Yep, both the slides are on the USB as well. Yep. Yes? Does the hashing algorithm matter for digital signatures? There's a certain set of them that are, I'll show you that. Again, I would go with the larger one. I showed you SHA-1 for examples. SHA-512 is like the most secure within that. That's generally what I would use. The signature stuff for digital signatures allows a certain number of signatures. I use SHA-1 to be easy. You got to look right here at the set hash algorithm and see, does it support all of those or not. And I imagine it's going to support all the ones that are already there, so it should go to 512, but I haven't tried it yet. So.
Which one do you use in practice?
In practice, I would use the SHA-512 because each one of those gets larger as far as what the hash size is. And some of the books, we talked about some of the resources too, talk about if you can't actually, for whatever reason, have that big of a hash, they talk about how you can just use a portion of that hash and that still works, and it's still more secure to use the larger one and take parts of it than to use a smaller one. Right. Okay. Otherwise, I've got a perf talk tomorrow if you're into web performance stuff. I'm actually going to try live website reviews. So I'm going to ask people, give me your URLs. I'm going to hit your site and tell you what you should do to improve your performance. And then later I'm going to talk about, what's my other one? I got one in the afternoon as well. Crypto, performance. Oh, mobile web. So I'm going to talk about approaches to developing mobile websites. That's tomorrow afternoon. So thank you very much for coming. Bit converter that you can use, and you'll see, I'm going to show you a couple different ways as we go through this particular session. You can kind of choose which one makes sense for you. I'll show you why this is useful to me later. But this bit converter will take that byte array and it takes each byte and gets its hex representation. And I just strip out all the dashes, so it just becomes a string basically of hex values that represent that hash. And then I display it. So now that it's a string, I can do a simple display. So that's pretty straightforward to use. Now I'm going to start talking about why would you want to use hashing and some of that stuff. Are there any questions before we go any further about any of the basics? Okay. So where would you want to use something like this? I like something called tamper-proof query strings. So the idea is I was working on a website, and this is pretty typical. I looked at the URL, and it had customer number on the URL, right? Well, everybody knows if you're using SQL Server databases, those are auto-increment. So I said, well, what would happen if I went up and changed my customer to somebody else's? And I did, and I can see it, but the other customer's data, which is obviously a problem, right? So the idea is it doesn't really concern me that much that the customer number is on the URL. It's not something I felt I should hide, but I definitely don't want you to be able to change the URL and see someone else's data. So the idea with this is we're going to use hashing to make this be tamper-proof query strings. So in other words, they could try to change the value of customer number, but if they did, I'd be able to detect that and I'd be able to reject it so they can't see another customer's data. Okay? So the idea is I'm going to take whatever query string I want. So I've got my link, I've got that query string with a customer number. I'm going to compute a hash of that customer number. I'm going to append that hash value onto the URL. That way when the next page gets it, it can look and say, I see the query string. I'll compute the hash. And if it doesn't match the one that was sent, then it can complain. Okay? And again, this has a lot of good uses within websites just because you don't want people tampering with query strings. I'm going to also show you why you want to use keyed for this. So let's start with a web page that just, so this one has a hyperlink on it. And I follow the hyperlink. Try to focus in at the top here. You can see I've got a query string A1, B2, C3. And if you look, I've also appended, the reason I did that bit converter and the hex is I knew I wanted to append it to a URL, so I wanted it to be safe characters for a URL, so I didn't have to worry about encoding it or anything. So the 1, 2, 3 stuff would have been there before, but this hash is the important part that's going to keep it from other people tampering with it. So we go look what that code looks like. So obviously now if I want to use this technique, I don't have to use this all over my site size. If I were to make even a single character change in that left-hand string, the actual hash function would be very different. Okay? And again, when we talk about using hash functions, I'm going to show you examples of it's okay if people see the data that I'm talking about, I just don't want them to tamper with it. So this is going to be when I want integrity. That's when I'm going to use a hash function. And I'll talk a little bit about being careful when you have a limited value range as we show some examples. So there's an abstract base class in .NET called hash algorithm. That's where all the derived classes are that support, and there's a lot of different algorithms available. I'm going to show you a couple different algorithms as we go. MD5 has been broken, so don't use that. Primarily, I use the highest level SHA algorithm, so the secured hash algorithm. But I'll show you some different examples in here. And there's also keyed hash algorithms, which just means not only is it going to compute a hash, it's going to use a key as input as well. I'm going to show you in certain instances why you want to do that. Okay. So let's take a look at some simple hash functions. So we've got a web page here. I'm just going to take some data. In this case, I've got this string. And if I were to run this, it's just going to compute a hash. So it's going to spit out this hash value. So if we look at what the code looks like, I'll spend a little bit of more time on this just because all of the cryptography is going to look pretty similar to this. So I want to spend time the first time and then I won't throughout the rest. But in this case, I'm going to use SHA-1 managed. So that's the hash algorithm I'm going to use just to make this simple to start. And I've got plain text string. Unfortunately, although you usually have strings in .NET, all the cryptography algorithms deal with byte arrays. Okay, so the first hurdle we have to fight is we can take it out of a string and get it into a byte array. There's lots of ways to do this. I'm going to show UTF-8 encoding is a pretty common encoding that people will use. So I'm going to use UTF-8 encoding and I just say I want to get the bytes for that plain text string. So all that has done is it's taken my string and put it into a byte array. The reason I mentioned the encoding stuff is later on when you start talking to partners or sending data back and forth or dealing with other people or other systems, how you encode that. If you encode that differently than your partner does, you're going to run into some problems. Okay? UTF-8, again, would be a pretty common one to use. So now that I've taken the string, converted it into a byte array, this hash algorithm has a compute hash function. All that's going to do is actually run the hash function against the data and return me another byte array. So that's actually the hash value for that given string. There's lots of ways that I can choose to display this. So again, it's a byte array. That's not terribly useful to me as far as displaying or passing it to anybody. So I want to convert it back into a string. And there's multiple ways to do this. I chose, there's a bin transit over the internet would be a concern for me. Whether I think people could access my web config file. So I'm going to talk later about how do you encrypt your web config file. If you're afraid somebody could get access to your web server and look at that file, I wouldn't want to have keys sitting in that file if I think people can do that. My personal stance, I treat my web servers in my DMZ like they're compromisable. In other words, I assume someone's going to be able to take over that web server, gain access to everything that's on it, and that's kind of the stance I take when I do security. Are you afraid somebody could dump out memory? I'm going to talk later about things that you store in memory. If someone can get on your machine and do a process dump, they can actually look at all of that data. So we'll talk about some ways to protect against that later. Can people modify pages? Can people reverse engineer your assemblies? If they get access to your assembly DLL and you put your password in clear string, for instance, they can just use ILDASM or any of the reflection tools and directly see all of your stuff. So it's important to sit down and think, for my site or for what I'm doing internally, which one of these things concern me so that you can make decisions about how you want to apply the right cryptography. Yeah. You obviously have company security policies. So I have a lot of policies about how we handle the data internally. Regulatory compliance, so I have to deal with PCI as a public-facing e-commerce website. And then layered defenses. How many do you think is enough? I'm going to talk about different things you could do for protection. And you kind of have to decide for yourself, how paranoid do I want to be? Do I have to do 12 things? Do I need to do 3 things? You got to kind of weigh that out based on how important your data is and everything else. Okay? Most important thing is don't try to write your own. Okay? A lot of people I've seen that think they can write their own cryptography algorithms. There's probably very few people in the world that can. If you're one of them that's in here, good for you. I still wouldn't try it. I mean, there's a lot of people that think they can, they can't. So these algorithms have been a long time. They've been tested. They've been proven. The .NET implementations have been used for a long time. So if you take nothing else away from this, don't try to write your own cryptography. The stuff is solid, and if you know how to use it properly, it's going to do what you're going to want it to do rather than try to do it on your own. Does that make sense? Okay, so we're going to start out with hashing and how hash functions work. So a hash function is a one-way function, so it's easy to compute in one direction, and I put significantly harder because I hate the word impossible when it comes to computers. So really difficult to go in reverse. Okay? So the idea is it's something that's fast. It's going to take, so I gave an example of some data here on the left-hand side. It's going to take that data, and it's going to compute a hash, and it gives me a fixed length string on the right side that represents what that data looks like. Okay? I like the term that it's a data fingerprint. So this hash on the right represents the data that's on the left-hand side, but it's a lot smaller and it's a fixed. Only particular pages I might care, right? If I don't show customer number on some of them, if they're product IDs, I don't care if you go spelunking around and find another product of mine. I just don't want you to see other customers' data. But any place I want to use it, I'm just going to call this hash query string. So if you see, I used to have just a normal hyperlink. Now I've got to actually construct the hyperlink, right? I've got to be able to compute that hash value. So what I do is I take the original query string I wanted, and I call this hash query string. And all this does is it says I'm going to take whatever the original query string was. I'm going to tack on a new name for my query string. That was that QTP val. And then I'm going to compute a hash like I did before. So let's go to this. This will look very similar to what we had before. I do my encoding. One thing you'll notice here, I'm using a keyed hash algorithm, and that'll become important in a minute when we talk about how someone's going to attack this. So I have a key that I'm reading from my web config. That key is part of the input. So not only is it hashing the string, it's taking this key value as well. And then it computes the hash like it did before, and then it converts that byte array back into hex for me. So that's how I set up the actual query string to go. Okay? The receiving page will, in this case I chose, if you look, I'm not doing anything special here. How many people in here, by the way, are web developers? I have an idea, or ASP.NET developers. Okay, if you've seen the base page concept before, I just created a base page, and the idea is that I can consolidate all of my code in one place. So this would allow me, if I wanted to, every query string on my site could have this type of support. And you notice, if you use forms authentication, your login page wouldn't have the hash, so you've got to be a little careful where you want to do this. So the idea now, the receiver is going to validate that query string. So the first thing it does is it says, if there's no query string provided here, there's nothing to do, right? Go ahead and return. Otherwise, I'm going to trim off the query string. I'm going to take it. I'm going to make sure that you actually sent a hash value. So I'm going to pull the hash value that was on the URL. I take the query string I just had, and I'm going to compute the hash of it. So I'm computing the hash of what I say the query string is now, compared to what it says on the URL. And these two better match, or we have a problem. Okay? So if I go back and show you a couple things, if I tried to cheat, let's say I changed that A value to 2, it's going to blow up. By the way, again, this is a demo where you'd never see a page like this in production for me. If you haven't heard of this before, there's actually a setting called deployment retail equals true. If you drop that in your machine config on your servers, it'll never show a page like this. And it also makes sure you're never running debug, that you don't have tracing on. So I just do that on all my production servers. All right, I think we'll get started. We're going to talk about cryptography today using the .NET framework. And my name is Robert Boedigheimer. A little bit about myself. I've been a web developer since about 1995, so I'm primarily, my day job as a full-time ASP.NET developer. I'm also a Pluralsight author. I've got a few trial cards that I've got a full course on cryptography there. If you're interested, you can stop up afterwards. I gave my blog, my email, my Twitter information. I also turned in the slides, and all of this code should be available on your USBs. Okay? But if you do have any questions as we go, feel free to ask. Things we're going to go over today, just talk a little bit of background about cryptography. We're going to go into hashing and how that works, symmetric algorithms, asymmetric algorithms, talk about how to use digital signatures. We're going to also talk about protecting your web.config file with cryptography so you can encrypt sections of it. We'll talk a little bit about key size and storage. How do you make the choices about what you're going to use? And then I'll mention some other .NET cryptography that's available. So a little bit of background. So the idea of cryptography, it's the science of keeping your messages secure. And we're going to focus really on, there's 4 different reasons why you might use cryptography, and it's important to understand which one you actually want, because that's going to help guide which one of the choices you're going to use, which technology within cryptography. So the one most people are familiar with is confidentiality. So the idea is that I want to be able to protect my data from being read. So for whatever reason, credit card numbers, things I don't want people to see, I'll use confidentiality. Integrity is when I want to verify that something has not been modified, and I'll show you some good examples of that. Authentication is where I want to identify and validate who a user is. And then non-repudiation is where I want a sender can't later deny that they sent a message, so we'll get into that with digital signatures. And the namespace we're going to use in .NET is System.Security.Cryptography. As I said, I'm an ASP.NET developer, so the examples I'm going to show you happen to fit in ASP.NET and happen to be web examples, but the same cryptography applies to any .NET code, so it really doesn't make a difference. Okay. Long list of considerations, so things that you need to worry about when you're looking at using cryptography. What's your goal again? Understand what it is you're trying to do, because that's going to map into the techniques you want to use. You need to understand how much your data is worth. So in other words, when we start talking key sizes and other things like that, if you need to protect your data for a long time, or if it's really important data, that's going to have you ratchet up the key sizes and be more secure, if that makes sense. We're going to consider what your primary threats are. So when you do threat modeling, like I would do for a website, I'd list out all the things I would be concerned about. Obviously, my data going